Another examples. One end of the line spring of the force constant K, right, is attached to the vertical wall. A line string is tied to the other end of the horizontal spring. As shown in the pictures, the string changes from the horizontal to vertical as it passes over the pulley of the mass M, right, in the shape of the solid disk of the radius equal to the capital R. So it means that this pulley will have the shape of the solid disk. The pulley is free to turn on the fixed smooth axle, so this one. The vertical section of the string supports an object of the mass small m. Okay, the string does not slip at its contact with the pulley. The object is pulled downwards a small distance and released. So if we hold this one, right, and push it downwards, right, and release, so it means that the m here will just go up and down, go up and down, go up and down, right? Okay, so now what is the angular frequency omega of the oscillation of the object in the terms of the mass capital M? So in this case, you can see that the mass M will just oscillating up and down, right, due to this spring. Okay, so we just want to find the angular frequency. So how, right? As I mentioned already before, right, if we just want to show that the object is moving as the simple harmonic motion or not, we need to find the equations of the motion of the object, right? And then let's say that the equation of the motion of the object just look the same as the fundamental equation for the simple harmonic motion or not, right? Okay, to find the equations of the motions, we need to find the we need to apply the Newton's second law of the motion in this case. But then before using the Newton's second law of the motion, we need to write down the free body diagram of the block M and then the pulley here. Okay, so let's just start from the block M. Okay, so now we have the block M, right? And then, okay, what else do we have? The weight of the block M equal to the mg. And then we have, let's say we have the tension here equal to the T1. Okay, we have the tension here equal to T1. So now let's assume that the block M is moving downwards direction with the acceleration equal to the A, right? So then in this case we can get that the mg minus the T1 equal to the M and then times the A. Okay, because we just divided downward to be the positive and the upward direction to be negative here. Okay, so now let's consider the pulley. Okay, let's consider the pulley. Actually it should move to this position. Yeah, right. Okay, so now let's consider the pulley. We have this pulley, right, and let's say that the center here is the axles of the pulley. Okay, then we have what? We have the tension here, right, equal to the T1. Okay, so don't forget that this is the same string, so tension must be the same, equal to the T1. And then coming to this point, it must be equal to the T2, right, equal to the T2, because I mean tension here and tension here must be different because the pulley has the mass. And what else do we have? We have the weight, right, of the pulley equal to the capital M and then times the G. And then finally we have the normal reaction force, that's the axles exerting on the pulley, right? Let's say the equal to the N. Okay, the pulley is okay as the mass M is moving down, right? So it means that the pulley will rotate into this direction with the angular acceleration equal to the alpha. So then in this case, let's define that the torque in the clockwise direction must be positive and the torque in the counterclockwise direction must be negative. Okay, so then okay, the same thing, we can just write down equation of the torque, right, for the pulley. Okay, then from equation let torque equal to the I and then times the alpha. Normal force and the mg do not contribute for the torque because it's just both of them just passing through the pivot, right? The one contribute for the torque is with the T1 and the T2. So you can see that the T1 will contribute to torque in the clockwise direction, so it must be positive. Okay, so the torque equal to the T1 and then times the R. And now for the T2, right, it's gonna contribute the torque in the counterclockwise direction, so it must be negative. So we have minus the T2 and then times the R equal to the I. The I here is the moment of inertia of the disc. So in this case, it's just the 1/2 times the capital M and then times the R square, right? Because we said that the disc, the pulley, right? Just where I said the pulley, right, has the shape of the solid disc. Okay, so the moment of the inertia is the 1/2 M and the R square, and then finally times the alpha again. So the alpha is just equal to the A and then over the R, right? So now the A here is the linear expression. Okay, so then this question we can just simplify. So you can see that 1R just cancel out, right? And this R cancel out to this one. Okay, then finally we have that the T1 minus the T2 equal to the 1/2 times the capital M and then times the A. That's it. So then how about the spring? Okay, how about the spring? Okay, so if we draw the free body diagram of the spring, right? Okay, so you can see that the spring is connected to the sting here, right? So if we try to pull the spring to the right hand side with the force equal to the T2, which is the same as this one, so it means that the spring try to pull itself back into the opposite direction, right, with the force equal to the K and then times the X. So in this case, because the spring doesn't have the mass, we can get that the tension T2 must be equal to the K and then times the X, right? And that's it. Okay, so now we have the three equations, okay, 1, 2, 3, and we have the three unknown variables, the T1, T2, and the A, right? Then we can just solve in this case. So how about let's just combine these three equations together. So we have, okay, on the left hand side we have the mg minus the T1 plus the T1 minus the T2 and then plus the T2. So this just on the left hand side. So now on the right hand side we have the MA plus the 1/2 capital M times the A and then plus the KX, right? Then the T1 cancel out with the T1, the T2 cancel out with the T2, right? Okay, then we can just rearrange the equations. Okay, we can get that okay, let's simplify this one first. We have the small m and then plus the 1/2 times the capital M. And now for the A, right, we can just write down as the d square x by dt square and then plus the k times x. Or we can get that the d square x by the dt square, right, is gonna plus the k and then over the m plus the 1/2 and the capital M and then times the x, right, must be equal to the m and then over the m plus the 1/2 times the capital M and then finally times the g here. Okay, and that's it. So now you can see that this one still doesn't look like the fundamental equation of the cyclic motion, right? because we have this term. Okay, because we have this term, but these two terms just fine. Okay, but then how can we get rid of this one? Okay, we need to use a technique. So let's define let's define here. Okay, so let me just define some variable. Maybe I can define this variable. Okay, equal to okay, maybe I can define this variable equal to the x. I'm not sure. X, and then minus some x naught. Okay, x minus some x naught, where this x naught is gonna be the equilibrium, okay, position of the block. Okay, the equilibrium position of the blocks, because right now we don't know the equilibrium position of the block yet. So let's say that this variable equal to the x minus the x naught. Then okay, if we find derivative, right, of this variable, oops, okay, by two times, okay, it's gonna be equal to the d square x by dt square. Okay, why? Because this is constant, right? So derivative of this term just go to the 0. So that's why we have only this. So now if we plug everything into this equation, then we have the d square and this variable, and then over the dt square, right, plus the k over the small m plus the 1/2, and then times the capital M, and then times, okay, so we have we need to find the x, right? And then we have this variable, and then plus the x naught, okay, equal to m, and then over the m plus the 1/2 times the capital M, and then times the g, right? Okay, so now let's multiply this into these two terms. So we have the d square, and then this term over the dt square plus the k, and then over, okay, the m plus the 1/2 times the capital M, and then times this variable, and then again, right, just plus the k, and then over the m plus the 1/2 capital M times the x naught, right, equal to this one. Okay, so now let's rearrange equation. Let's just move this to the right hand side. So we have this, okay, we have this, and then equal to this term, right, and then minus this term, okay, minus this term. But now we say that we need the whole thing here to be equal to the 0, right? We need the whole thing here to be equal to 0. So just clearly seen that if we need the whole thing here to be equal to 0, then the x naught, right, it must be equal to what? It must be equal to the mg, and then over the k, and that's it. Okay, so that's gonna be over x naught here must be equal to the mg, and then over the k. So it means that this is gonna be the equilibrium position of the block. Okay, equilibrium position of the block. Actually, you have seen this type of the things already from the vertical spring mass system, right? Okay, from the vertical spring mass system, that we say that okay, we have here, right? So generally we have the spring hanging vertically, and then if we just put the mass to one end of the spring, right, so the spring will extend into this direction, and this will be the new equilibrium motion of the spring, right? So we can get that the mg equal to the k times delta L, or we can say that delta L here equal to the mg and then over k, right? So this extension of the spring is the new equilibrium motion of the spring of the block. Okay, so we just got the same thing here. It's just the mg over the k. Okay, so then finally, you can see that we have the whole things here. Okay, we have the whole things here, and then equal to the 0, right? And that's it. So now this equation just look exactly like the fundamental equation of the simple harmonic motion, right? And we can say that this term, it must be equal to the omega square, right? Or we can get that the angular frequency in this case, the omega, equal to the square root of the k and then over the m plus the 1/2 and the capital M, and that's it. So that's gonna be the answers.